Great. All right, hello everyone and welcome to today's webinar, Conversations in Energy Storage Integration. Just a few housekeeping notes. Controls are located at the bottom of your screen. If they aren't appearing, you can move your cursor to the bottom edge and see them there. All attendees are muted, but we invite you to type your questions into the Q&A box. However, I encourage you to save your questions for the panel discussion, unless they're really specific to the speaker, just to energize that panel at the end of the session. We are recording today's webinar and you'll receive a follow-up email within a few weeks with a link to view the recording. And with that, I will go ahead and kick it over to today's moderator, Craig Turchi. Craig, take it away.
Thank you. So I'm Craig Turchi. I'm the moderator today. I won't go through a detailed introduction of myself again, but I'm an engineer at NREL in the Thermal Energy Technologies, Thermal Energy Science and Technologies group. So our session today will follow the same kind of format as we had yesterday. If you were involved, we've got half a dozen speakers, and each of those will give an initial presentation. And we'll follow that time with a 1 hour long panel discussion that will involve all the speakers. I will introduce the individual speakers when their slot comes up, so I won't go through that all to start with. But Nate Blair is going to give us an overview to begin this session. Then we'll have 20-minute presentations from each of the other speakers. And as I said, we'll follow that up with the panel session. Please post questions into the chat box as indicated. As we go along, we'll compile those. If we have a speaker finish before their time slot ends, we'll address a couple of questions, but most of them we expect to have during the panel session. So with that, I'll move ahead and go ahead and introduce Nate, who's going to give us an overview. Nate Blair is a group manager of the Distributed Systems and Storage Analysis team at NREL. He's been in this position, well, he's been at NREL for over 10 years, and he's been working in developing energy and energy efficient system modeling for over 20 years. Nate's worked on software tools used by researchers at NREL and around the world to model renewable power systems, as well as the electric grid itself. And these include things that many of the audience may know, like Transys, Reeds, SAM, PV Watts, and others. Nate's got an MBA and a master's in mechanical engineering from the University of Wisconsin at Madison, and his bachelor is in physics. So Nate, you'll take the screen. The other presenters can go ahead and turn off your screen if you'd like, and we'll listen to Nate.
Great, thank you, Craig, and thanks for that introduction. I think the focus of my quick presentation is sort of on the future of energy storage, the sort of second part, while touching on some of the emerging technologies, but we're most of the way done, I would say. We have a summary report still to come out, and we just did a webinar on our 6th publication coming out of our storage future study, for which I'm the PI and coordinating a bunch of really excellent researchers. And let me just dive right in here. I always like to start with this, why energy storage, why now, why do we care about the future of it? And I think this audience probably knows as well as anybody the dramatic drops in a series of key technologies, and these will, the growth and deployment of these are going to be a large part of what drives the future of energy storage. And we've had past dramatic price reductions. This one is here for batteries, but we anticipate additional price reductions for long duration storage options as well, past 10 hours, and a variety of technologies to play in that, and that comes through in our work. But it's an exciting time for energy storage broadly because of the various effects of cost reductions as well as policy changes as well. So this is a high-level slide on the Storage Future Study, looking out to 2050. We have released a series of reports looking at this issue from a conceptual standpoint, to a grid level standpoint, to a distributed storage standpoint, and I think across a range of scenarios. And our one key conclusion is that under all the scenarios, dramatic growth in grid energy storage is the least cost option. So we're anticipating significant increases in storage. We have released, as I said, a series of reports already, and I'm going to touch on a few of the key conclusions. I don't have much time today, but as you can see here, and these are all available on the Storage Futures website. So if you just Google NREL Storage Futures, you'll get to the location for all of these. But as you can see, quite a bit of work, quite a bit of effort on all of these. And we have one remaining one, which is the key learnings report, which is drafted and in review at this time. So one of the things that we did in last year, and so some of the data might be a little bit out of date, but is trying to figure out, where some of these technologies lie on a kind of a capital cost related to power and a capital cost related to energy. And as you see, as you move along or to the dots that are closest to the vertical axis, those are technologies that are likely more competitive for long duration uses. So adding a little bit more energy or kilowatt hours to that technology is cheap. Adding more power is perhaps more expensive. The zone along the bottom there is technologies that are likely more competitive for shorter duration applications. So you can see the flow batteries and so forth. Lithium ion batteries is at the midpoint there, and obviously as you go to the lower left, you start to say, oh, this technology is perhaps good for long duration and shorter duration. And then as you kind of go up and to the right, we have a series of emerging technologies that are likely to probably require some level of cost reduction as we go into this area. And note that some of these cost points are anticipated. This is what this technology could get to as it gets to be commercial scale. A number of these, as Craig's going to talk about, and others are more on the emerging scale point of the continuum right now. So we ran a series of scenarios looking at a range of battery costs, a range of durations. As you can see on the left, as we go out towards 2050, and we get up to kind of in the 60 to 70% variable renewable range. We're not looking here at 100% renewables. But we see that the system starts to deploy short duration first, longer duration, and then longer duration, 6 hours, and then 8 hours kind of after 2040, and then 10 hours. And as you get to these higher and higher levels of VRE penetration, we see more and more longer duration storage. And so as you get out to close to 100% variable renewable energy, you'll see a need or an optimum in the system with even longer duration storage. On the right, you can see that the cost of battery storage in this case really drives how much is optimum. So if you have a high battery cost case, which just comes down a little from today's costs, then you get less storage capacity, but still quite a bit more reference case, and then low battery cost case, and then that's the range of all the cases that we looked at. So quite a big range of potential storage, but all of them quite a bit higher than today. I would say also that one of the things that we talk a lot about in this report is the interaction between PV deployment and storage deployment. So as you get more and more PV on the grid. If you're familiar with the term, the duck curve, you can see that the demand during the day shrinks, and that starts to really shrink the peak of the energy demand in the afternoon. So this is just for California, but it's locally in California that you start shrinking that peak, and that reduces the needed duration for storage or for peaker plants, and that reduces the cost of the storage, and so makes storage look more effective in those situations. And on the right, we see that as we move from 2020 to 2030 in this particular scenario, we're moving, solar starts to move when you're charging and when you're needing to discharge, and the length and the size of the peaks as well. And so that starts to be advantageous for batteries as well. And then I think this is another one of our key conclusions is the average duration of new storage as we get to higher and higher levels of storage capacity. So you can see that as the total amount of capacity grows, and that's likely in conjunction with higher levels of solar and wind as well, the average amount, average duration, so, and not the marginal duration, which would be even higher, but the average duration really starts to increase. And so you see a trend as you go forward here towards longer and longer duration storage. And that comes out sort of in our conceptual analysis, which looks at, as you want to move to higher levels, you start time shifting with the solar in particular, but also potentially with the wind in some situations. Behind the meter, we have a report that looks at not only the economic potential, which is in gigawatts of 2-hour batteries in this case, but then kind of the anticipated deployment, which is much lower. And that's because at the moment, we're looking at pretty long payback periods for distributed storage. Now, those payback periods go down if you really value backup power, and we're seeing more and more of that in different areas of the country. Or if the economics change, if distributed PV and distributed batteries get cheaper, the adoption level increases. And so there's a lot of dynamics here, and I think we have a lot more to explore there on the distributed side. So that's my very quick overview for Craig. Hopefully that was about the right duration. Happy to answer questions, and hopefully that helps set the stage for the conversations to come.
Thanks, Nate. Yep, you're right on time. Just one quick question. So you talked about batteries. You used the term batteries in a lot of these cases. Is your analysis unique to batteries, or is it really energy storage? You could think more generically.
Right. And we make that point both in the section of the report that I showed that kind of looks at all of those technologies. We do dive into some of the details on some of the emerging technologies. We make the point quite clearly that if there are other technologies that exceeds probably a bad term, but are cheaper than lithium-ion batteries going forward, then that is what we would anticipate building out into the market. And again, we're not looking here per se very closely at very high penetration, kind of 90+% renewable energy or variable renewable energy penetrations, where you really get into this need for long duration storage. Okay. So either one of those situations, significant price reductions or very high need for longer duration storage.
Thank you.
Sure.
All right, we're going to transition over to Dr. Sarah Kurtz now. So Sarah, you can start to load up your presentation. Sarah is a professor at the University of California at Merced in the School of Engineering. She obtained her PhD in 1985 from Harvard University, and she now works at UC Merced. She went to UC Merced after about a 30-year career at the National Renewable Energy Laboratory here in Golden. She's known for her contributions to developing multi-junction solar cells, supporting concentrating photovoltaics industry, and leading efforts on PV performance and reliability. Her work has been recognized jointly with a jointly received Dan David Prize in 2007, a Cherry Award in 2012, and a C3E Lifetime Achievement Award in 2016, and induction into the National Academy of Engineering in 2020. At UC Merced, she is working to support their energy transition through a variety of studies, including a current effort on long duration storage. And when I came back to NREL in 2008, one of the things I really remember was a conference I went to that Sarah was speaking at, and I didn't know a whole lot about what I was talking about at the time, but she helped me out, and I always remember the assistance she gave me in that presentation. So a great researcher and a wonderful person too. Go ahead, Sarah.
Thank you. That was a very nice introduction, and it's a real pleasure to be back with all of you. It's both an honor to be invited to be part of your strategic conversation today, and also really special to reconnect. As I look through the list of the participants there, I see a few familiar names, so maybe I can reconnect with some of you I haven't spoken with in quite a while. I have more than enough slides to present for 20 minutes. But I wasn't sure if this is a very complicated conversation, and some of the other panelists will be talking about some of the things that are part of this. So I apologize if it feels like I'm going through really quickly, but during the panel discussion later, we can always return to the slides that I've skipped over. So I'm going to start by talking a little bit about storage from the grid perspective. That I was asked to focus more on the grid, but of course the grid includes kind of everything. And I'll talk about how storage depends on the renewable generation profiles versus the load. I'll talk some about the storage technologies. As you saw on Nate's slide, there are many technologies out there. I will run through a list of them, and then I'd like to try to see if we can think about, if you step back, if we've got like 20 different options out there, how do we kind of think about them? And talk about which ones are likely to be growing in the future. And then finally, I'd like to talk about the wild card, the alum cycle. I haven't heard many people talking about this. I think NREL really should be talking about it, and you may all be aware of it. If so, then maybe it's not a new thing, but if it's not known to you, I think we should talk about it a little bit. So if we're looking at how the grid works, the standard way that people will model energy storage is to look at, you've got the electrical grid, and you think about, in general, the electricity goes from the grid to the load. You can also look at storing the energy by storing it locally. But more often when we're doing the modeling, we're looking, and I should say, if you're storing it locally, that's more like, we call that demand management. But we more commonly model it for the grid to create a reservoir, and then we take electricity from the grid, we put it into the reservoir, and then later on we put it back in. But the demand management piece here is a possibility. Now, Lawrence Berkeley National Lab did a study that suggested that the loads that can be shifted at a cost that's less than the cost to use storage is about 6%. So this can be a valuable tool, but it's not going to get us where we need to go. The other piece that I want to talk about some is what I call cross-sector storage. The cross-sector storage, you can take electricity from the grid, and you can, for example, run an electrolyzer and use hydrogen for transportation. Then later on, you can take hydrogen that's maybe being used for transportation. It could be actually hydrogen that's been made from natural gas, blue hydrogen or something, put that back onto the grid. And so this means that we don't need, whereas here we're keeping track of how much energy we put into the reservoir and how much we take out. If we think about modeling cross-sector storage, then we end up with the possibility of putting in more than we take out, or putting in less than we take out. And it gives us an added knob to turn. And I'll show you in a few minutes why I think that that's really important. The other thing about talking about the energy storage is looking at the time scales. So you have the things that are shorter. Nate's just given a very nice introduction on his graph that showed the difference between the power and the energy costs, and how, depending on which quadrant you're in, you're more competitive in these different regions. So people talk about, like, how much do we need of these different types of storage? We need something to meet the peak during the day. We need to get through the night with solar. And then if we have cloudy days without much wind, we may need low days or weeks. Then we may need, for seasonal storage, we may need a much larger time. And so the modeling time that we need to use to understand these different effects will change. So I wanted, in terms of the cross-sector storage, it's useful to back off and kind of think about how much storage do we have out there today? And what I did was to go through, you can look at the EIA, and we've actually published a short piece in which you can see this and get the reference for where we got the data, but it's just, you can go online and get the EIA data. If you look at the amount of energy that we're storing today and convert that into how much, how long it could power the electricity grid, it's about 5 months. So the question I ask to all of you is, when we move to a renewables driven grid, will we need more or less storage than we do today? You can make the case for either. So my conclusions about when you're looking at how to model in terms of the energy flows, in addition to using standard storage, it's useful to think about installing electrolyzers and monetizing the hydrogen for use elsewhere, and looking at it as a cross-sector storage capability. And then in the timescales, it's going to be useful to model the full year of weather data, and also useful to be able to compare different weather years if we want to fully understand the seasonal storage. And what I was showing you in this previous slide here is that these overlap. So if you have some of the storage that's a self-contained storage versus some that's cross-sector, they may be competing for these tech applications that are in the middle. And you may find that sometimes these are satisfied by one type and satisfied by another. I wanted to talk just briefly. I've got a whole hour or 2 hours worth of talks I can give on this particular topic, but I think you're all aware that understanding the storage you need depends on understanding the generation profiles you have, and specifically how those generation profiles relate to your load. In Colorado, you can balance the wind and the solar generation in order to meet your seasonal needs. Do be a little careful if you're using EIA data. They no longer report real data for most of it. It used to be they reported real data for more than half the plants. Now they're only reporting real data for about 10% of the plants. So the fact that Colorado's wind used to peak in the winter and now it doesn't, I think might be an artifact of the EIA data sampling and not the actual change in the weather, but it's possible that the weather's changing. It'd be useful to figure that one out. In California, we have a problem that the generation from wind currently is also following the solar pattern. And so now if you compare this to the load profile and the fact that we might be adding more heat pumps, we are going to have a real problem here in the winter in California. So we may be trying to bring things in. And if you're interested, we've got a bunch of, we've got a paper here that is on that QR code. So we might just talk a minute about how to model cross-sector energy storage. The Lawrence Berkeley Lab study, as I mentioned, reports that 6% of today's load may be able to go into demand management. But my suggestion is that if we started using electrolyzers to generate enough hydrogen to run fuel cells for trucks and lots of other things and industrial power and things, we could, one of the potential scenarios is that we could end up with 50% of our load being electrolyzers. And that would give us a really big flexible load. If you had a 50% flexible load, then demand management becomes a big deal. And if you look in California, the difference between the load curve and what you get from solar, you can see that there's big opportunity there. So I'm going to move Actually, I'm going to move through this slide. We can come back to this. It's talking about the strategy with using electrolyzers. In the interest of time, then I'll move on to some of the discussion about the different storage technologies. I think everybody knows pumped hydro is king today. There are new projects coming online, but these are difficult projects to do. We may hear more about those in a little bit. There are other forms of gravity storage. You have Energy Vault, for example, who's doing gravity storage with big blocks. Then there are a whole set of new kinds of batteries coming out, not that are beyond lithium ion, flow batteries, looking at different chemistries, metal air batteries. And Form Energy has recently announced that they're doing 100 megawatt 100 hours. So it's 100 megawatt hour and 101 megawatt. So it's designed to be able to charge up and then deliver the energy for 100 hours compared to what Nate was just showing in the modeling. That's a way longer duration battery than what some people are talking about, but others are talking about that this is going to be important. Another interesting one is using exfoliated metal. In this case, they will take the zinc, and as the zinc is deposited, as you reduce the zinc and it builds up on the electrode, then every now and then they wipe it off and the zinc falls to the bottom of the container. And you can then just collect a whole bunch of zinc down there and then later on use that zinc to drive the reverse reaction. So there are lots of different flavors of these. In general, all of these require chemicals that you have to then talk about the cost of those chemicals and the scaling. Form Energy's point is that they can use very cheap iron, and that's why they can get to these very long durations at low cost. I'm not going to talk about Malta because we have a speaker from Malta, but I didn't want to be dismissive of that, just to recognize that others, and also I see Ziwen is on the call. I also won't speak because we have another speaker about the thermal storage. I won't talk, but you have your own study here at NREL on the thermal storage. And there's also Antora Energy, who is doing work on thermal storage. There was a note about liquid air, and it's really an interesting question now. You're going to see one of the themes I'll talk about here is, can we've used water historically as a way to store energy. In the future, will we use air and rock and things like that? Highview Power has been doing the liquid air. They've been a leader in the field, but I do notice that recently they've gone quiet. I'm really interested to hear from any of the rest of you if you know what their status is. Now, QuidNet is a very interesting one. They drill down deep into the rock, maybe a kilometer down or something, and then they do a horizontal fracture. Then they stabilize that horizontal fracture. It's very important that they stabilize that because you don't want to continue. You want to have a well-sealed shape down there. They call it a lens. And then they pump water down, and they actually pressurize then the rock down here. And so it lifts up the rock on top and pushes down on the rock underneath. So when you think about it, if you're looking for a large energy reservoir, what's cheaper than being able to use a huge chunk of rock down there that you don't have to go and mine or do anything? It's just right there. So this is a really interesting one in terms of being able to do large quantities of energy storage without having to figure out where you're going to get all that rock. Now, it does have some concerns that people are working through about. Everybody I talk to is worried about earthquakes. The idea does not work if the water leaks out of this cavern to contaminate nearby water sources or to create earthquakes or things. The concept simply won't work. So they have to get it so that this is a stable little cavern down there that does not leak or change in any way. Now, HydroStore uses a similar kind of, well, it's actually quite different in the concept, but what they do is to drill down, and then they actually send mining equipment down and open up some caverns down there. And a really interesting part of what they do in a standard compressed air, and there already utility scale compressed air storage working out there. So we know that compressed air can work and can be useful. But what they've done here, one of the problems is if you have a big cavern and you pressurize it, then as the pressure releases, the pressure goes down, and then your ability to use that stored compressed air decreases as the pressure decreases. But what they do is to put a water shaft down, and then they use water as a bladder here so that they can, and the pressure of the height of the column of the water pushes down here so that you can keep a constant pressure on the air. They're getting to be actually a pretty decent size and are currently very well funded. I've been very impressed by their people. So they may be getting to the point where they can scale up. Then there's another company here called Augwind, and they're using the ground as well. And so they take these tanks and put them underneath of the ground, but in a shallow way. So it's very similar to some of the others, but they're doing it in a very, whereas QuidNet is very deep and HydroStore is going down some substantial difference. These are down just like a meter or something. And then these can be pressurized, and they're storing these. They're getting ready to do their first project starting in California. Then there's another one here that's doing Energy Dome. It's in Italy, is doing compressed carbon dioxide. So this is very similar to the liquid air sort of concept, that you can, if you can compress the air, and instead of having it a high pressure air, which is still takes quite a bit of volume, if you compress it to the point where the CO2 is now in its critical state, it becomes a liquid, the volume comes way down. And so then you don't need the huge equipment. They do have this big dome they use for storing the CO2. They have a closed cycle, so the CO2 isn't going in and out of the atmosphere. It uses mostly off-the-shelf equipment, and they're also just getting started here. So I just want to note, I haven't gone into great detail on most of these, but there are lots of different kinds of opportunities to go beyond the lithium-ion batteries, which are very important and are going to be very important. I don't in any way want to belittle those, because they're already playing major roles. Here in California, you can see that we are charging the batteries at about 1 gigawatt. Pretty much every day, there's some time that they're operating about 1 gigawatt. I also want to note, you've got another talk coming later on hydrogen, but hydrogen is such a huge thing. I have the slide in there, but I'm not going to talk about it because we have the other speaker on it. So in terms of conversations that we might have, if you're looking at where's this technology going, we have our standard metrics. You talk about these for every technology: cost, efficiency, and lifetime sorts of metrics. So these, and we can go through and rate each of the different technologies on how they do in each of these. And if you can find one that's totally low cost, almost 100% efficiency, and very long life, that's going to be the winner for everything. But in general, what we have is a mixture of some that maybe do better on cost or better than efficiency or better on lifetime. Then I'd also like to suggest we think about like the difference between liquid air. When I first heard about liquid air, it's like, wow, that's really cool. This sounds like really interesting. It uses all off-the-shelf, well-known equipment, and there's plenty of air out there. You can cool it down. But when you do the cryogenic air, if it sits there, then because it's a cryogenic temperatures, it's going to be leaking. And it's also just more the equipment that's going to be used probably for cryogenic things it's likely to be a little more expensive. If you can do a similar concept with compressed CO2, where you can get CO2 into its liquid state at room temperature with a manageable pressure. It's actually high pressure, so there's still some challenges. A question, if you compare these two options, excuse me, which of these is likely to be a winner in the end? And so I'm very curious to see. I don't know much about this new compressed CO2 technology and whether the company that's doing that has a viable business plan and a viable technology, but it's interesting to me to think about the difference. In general, if we think about the working fluid, what's the fundamental difference? And I'm not a mechanical engineer, but those of you who are, what kinds of efficiencies are we likely to be able to achieve if we have a working fluid that's, say, water versus gas, or like if we have liquid CO2 is CO2 is a working fluid going to have some advantage over, say, using a gas, or is it all the same? So that's a good question for you mechanical engineers to give me. You can give me an answer. Maybe you know off the top of your head, or maybe it's a research problem. And in general, if you're looking at the storage medium, so certainly lithium ion batteries are fantastic. Trying to scale them to that size where we might possibly need 5 months of storage, that's a huge amount. Are we going to be able to make something that big? If you start thinking about doing 5 months worth of storage in something that's more like air, water, rock, does that become more feasible? Maybe it doesn't, but maybe at least the challenges become quite different. And so thinking about how we use air, water, and rock as our storage medium compared with using chemicals is just a high level question we might talk about. So from the grid perspective, I think a couple things we should be focusing on when it looks like I'm at time is the scalability and the flexibility. And let me just say the wild card, I wanted to introduce the Allam cycle. What would you think is the future of the world if we have a technology that has no carbon dioxide emissions? Maybe it could be negative carbon emissions if you're looking at using it with biomass, no criteria pollutants, potentially cheaper than today's natural gas plants, smaller footprint than today's natural gas plants. If you run it from biogas rather than natural gas, it has the negative. What difference would this make to the grid? And if you're interested in this, you should go to this link. But the question I would ask for all of you is, do we just view this as a threat, or do we view this as an opportunity for someone at NREL? And I think with that, I should stop because I think I went over my 20 minutes. I apologize. It wasn't
Thank you,
watching.
Sarah. No, you're right on time, but we will move forward into our next speaker. So as a great overview of the different types of technologies that we're considering for energy storage, and it does make it a very interesting landscape for people that are working in these different technologies. And our next speaker is Jean Barones. She is the former supervisor of hydrogen strategy, infrastructure, and production at the California Energy Commission, or the CEC. So Jean has worked at the CEC from 2009 to just last month, actually, 2021, ending her tenure there, managing projects in distributed energy resources, including stationary fuel cells, biofuels, and conducting economic benefits on those benefit assessments on those technologies. Jean holds a master's degree from both George Washington University and Johns Hopkins. So right about on time here. If you just switch us into presentation mode, Jean, I think we'll be good to go.
Okay, thank you, Craig. Where is presentation mode?
The little, you were right down in the lower right corner, the little podium looking icon. Looks like a little screen. That's the guy.
Thank you.
That's it. Perfect. Okay. Thank you, Jean. Take it away.
Great to be here today. And I come from quite a different perspective, which is about the adoption and acceptance of these alternative fuels. Of course, grid storage is a major part of looking at the adoption of alternative fuels, and I'll touch on both sides, both aspects, which I think are interdependent. I did participate in the Hydrogen Technology Advisory Council, which was established by EPAC 2005, and in the HTAC, it's called, in their final report in 2019, and in their observations of the EPRI-McKinsey Roadmap for Hydrogen, the HTAC commented that systems modeling of hydrogen in the electricity grid is very, very important, and gives upbeat notes on the potential for systems modeling across many sectors in use, applications, for transportation, for materials handling, for grid storage and just the general infrastructure build out to parallel the electricity grid. Another point that I think builds on the work ongoing at NREL, the storage study soon to come out, is Mark Ruth and a number of other experts at NREL's and other energy labs looking at the scenarios for affordable hydrogen production and again, transport, storage, and use. And here the NREL and the other lab teams look at some of the possibilities of changing the market potential for hydrogen based on resource costs and adoption. The value of that work, I want to stress, is very important to people like myself who look at adoption and acceptance of these technologies, because it's a neutral body of work, it's understandable, and it has been applied. Looking at what's affordable, what costs the supply community wants to sell at, and what costs the purchasing community wants to buy at. It's really looking at the costs. And the HTAC and NREL both, and McKinsey's and EPRI's roadmap, all three look at risk assessment as a key part of the decision set for hydrogen storage. And the three of the really important consortia developed and funded and carried out, and their work carried out by U.S. Department of Energy in materials, the HIMARC, the HMAT, materials compatibility work are very important, and HTAC applauds those and applauded those in their final report to the Secretary of Energy, as they did the H2RAM consortia, which is about risk assessment, looking at safety requirements and standardization of evaluation of materials and equipment. So I recommend that these consortia march on and continue to evaluate. So Jen Kurtz and Rebecca asked me to look at, the integration of research and in design and hybrid storage. And so I thought through the last 10 years of California's investment in transportation and local storage and remote storage and hub and spoke configurations that were used to deliver hydrogen fueling outlets, and to me, a key point of how we integrated research, design, and storage was the use of a tool developed by NREL. This is the Hydrogen Storage Capacity Evaluation Tool, HISCAPE. The tool is presently referenced by the California Resources Board Low Carbon Fuel Standard Hydrogen Refueling Infrastructure Program. I know that was a lot of acronyms, but it's a capacity-based, a nameplate capacity-based program for crediting. And I want to emphasize that this tool assists developers and suppliers and the vehicle providers with evaluating their true, as close as possible to their true cost of rolling out fueling outlets, because it assists in evaluating the value, potential value of credits for their nameplate capacity. So going into projects, designing projects. This tool is useful and it's open source, available in the public domain. And so I just want to emphasize that the research aspect of all the options that Sarah just mentioned is fabulous, and keep going, but looking at the actual cost of implementation is maybe another side of the work. And I know that cost assessment can take on a life of its own, and it can be a study unto its own. But the user community of the research and the tools likes to have a neutral tool and a neutral platform that assists in their cost assessment. So just want to encourage more of the open source systems that are available for estimating costs. And another current ongoing effort is with the Asia Pacific Economic Cooperation, APAC, you may know of, work, which just 2 weeks ago issued an international survey on the value of an international standard for defining low carbon hydrogen in all applications. This APEX standard is something that the IPHE from the US Department of Energy is likely to read about, participate in, and possibly help NREL researchers understand the varying definitions on a global basis. And so the potential for driving the investment in the use of hydrogen, be it at an application level, be it at an energy storage level, could expand with international understanding and definitions of what low carbon hydrogen is, how it's produced, and how it's used. And my third point is in the area of application development, testing, and deployment. So the H2 at Scale initiative, which both the NREL study by Mark Ruth and others, and as funded by the US Department of Energy, provides a tremendous way to articulate the cross-sector philosophy articulated by HTEC and in the McKinsey-EPRI roadmap, and by all of us. And so today I know all of you are so intimately familiar with some of the projects, but I just want to point out in some of the mobile platform projects, the liquid hydrogen on board of the aerial vehicles out of the state of Washington is coming along, and a press release will be issued in a few months on the status of that project. The H2 rescue emergency truck under work at Cummins is also progressing. This is a combination battery fuel cell truck that will deliver potable water and power to emergency events and situations. And then the California network of stations for light duty refueling has grown significantly, up over 50 stations, filling nearly 10,000 cars a day. These all use hydrogen, and the supply in California is becoming more diverse and is becoming bolstered. Upwards of 70 ton a day supply chain is possible and planned for 2023-2024 timeframe. So these areas of cost assessment, articulating costs, articulating the definition of what is low carbon hydrogen so that we have an international understanding of what today is quite varied. And then looking at the load of the applications under development, and I only mentioned 3 out of numerous applications. So the load and the supply is there. And so if you look at that load as a user of the potential of the supply, dedicated, I agree, but as a part of the picture of the need for hydrogen, it's probably valuable. So I just want to say that a challenge, I was asked to look at one challenge over the next 5 years. So I'm going to suggest more of what the HTAC final report articulated, which is a stepwise progression, and the EPRI-McKinsey roadmap articulates this too, stepwise progression to 2030 and beyond, and looking at the cost advantage of integrating hydrogen with grid storage and all the options that Sarah brought up show so many options and the storage study will show, I'm sure, many, many options. But to hit on the economy of scale possibilities across the various sectors would be key. And then choosing those projects that have the wide range of applications. In the area of medium and heavy duty, you have a greater load than the light duty in the area of transportation, obviously, maybe 35 kilograms on board for the larger tank sizes. So there'd be a large draw on the supply and the load. And then to also keep in mind the hydrogen shot of $1 a kilogram in 1 decade to serve all the new markets. So it's again the need for the cost advantage studies so that all these boats rise at once and all of them benefit together. This concludes my presentation, Craig.
Thank you, Jean. Yeah, you've wrapped up a little early, but that does actually put us right back on time. So I think rather than take any questions right now for you, we'll save that for the panel session so that we are back on our schedule. So we'll move to our next speaker. That is David Havard. He's a senior global project manager with GE Renewable Energy in the hydropower sector. So for the hydropower business within GE Renewables, David analyzes the technology portfolio versus current and future market requirements and competition. And doing this, he makes recommendations on future strategy and resource allocations for GE. David has a degree in economics from Durham University. And so he'll give us an overview of pumped hydro storage, which I know several people have already asked about. Thanks, David. Go ahead.
Thank you very much, Craig. Can I just check that the audio is okay?
It looks good. You sound good too.
Okay, great. And you get in the full screen. Okay, well, look, thank you very much for the introduction. Thank you to you all for giving me the opportunity to speak. You can maybe guess from my accent that I'm going to give you an international perspective. I'm actually sitting in Europe with a global responsibility for hydro, including pumped storage hydro. And really, that's why I'm going to speak today. I work very closely with my colleagues in the US on the pumped storage market and the perspectives. But we thought it might be interesting for you to have someone sitting elsewhere with a full picture of what's going on throughout the world in terms of bulk energy storage. So that's why you're going to have to listen to me for the next 15, 20 minutes. I will then talk about pumped storage. I would draw your attention when we talk about what are the different technologies going to be able to do to work together for the energy transition. I think it's very interesting to look at the graph, which is on the right-hand side of the slide. It's a log scale, a little bit similar to the one that Nate showed earlier. We're not seeing cost though this time, but we are seeing the energy storage capacity, gigawatt hours on the vertical axis, and then megawatts power on the horizontal axis. And basically you can see different discharge rates, which are represented as diagonal lines. And really what I'd just like to call out on this slide is that the bulk of the pumped hydro in the world today is typically already with around 6 to 12 hour discharges. So it fits very nicely already between, for example, high power, short duration batteries, and then, for example, power to gas. We talked about hydrogen just before. So sitting very nicely in the spectrum, let's say, of storage possibilities. Overall in the world today, there's about 150 gigawatts of power of pump storage. If we look at where those fleets are, you can see the upper band is representing the US. We're basically looking at gigawatts installed on the vertical axis and then the years on the horizontal axis. So we can see that the fleets of pump storage really took off in the 1970s and then in the 1980s, and that was particularly true of the US. The US has got a fleet of about 23 gigawatts of power, which is 550 gigawatt hours of storage. So if you do the math very quickly, you can see that that gives an average of about a day's worth of storage per gigawatt. But it is let's say the trap of using averages. Within that, we've got 1 or 2 power plants with a great deal of storage, and then there are others which have got, for example, 6 to 8 hours. But just to give you a perspective, and I think it's important to remember those numbers, 23 gigawatts and 550 gigawatt hours of storage. You can probably guess from this graph, so the stripes, we don't quite get the stars, but the stripes are there to represent the US. The blue is for Europe, the red is for China, and then yellow is a combination of Japan and South Korea. So all those places put a lot of nuclear, put a lot of thermal fleets down in the 70s and 80s, and they basically used pump storage as a way to regulate those facilities. The US did have the world's biggest fleet of pump storage, but the US hasn't built any really of any significant size for several decades. And so now China is the world's biggest fleet with a very ambitious build. Nevertheless, worldwide, it's expected that the fleet in gigawatt terms will double in the next decade. And I won't spend a lot of time on this next slide, but it's just to show you 1 or 2 of the hotspots, let's say, in the world. One area where I'll just draw your attention, it's India. I find it interesting as well in the context of the talk that we're having today. Their pump storage has been used in combination with wind and solar. There was a question about this already in the chat. And in fact, it's been used as a means to firm up the other renewables and to guarantee a certain level of supply for 6 hours of the day. So it's quite an interesting concept. We're seeing it in India only for now, but very clearly a way that pump storage or bulk storage can firm up the other renewables for critical hours in the day. I realize that everyone on this call knows this slide, so in fact, I won't spend too much time on it. I think we all agree that energy storage is a key enabler for the energy transition. Others have already spoken about the things that are at stake. So I suggest to go quickly on this one to save time, or to perhaps spend more on the technology piece of pump storage. The final slide before I get there is just to show you a picture as well of other continents. We can already see in the green areas, the green sections of these bars, what's already, for example, in 2018, the penetration of wind and solar, for example, and what's the projection towards 2028. You can also see the blue bars are showing the existing hydro generation. I'm going to talk to you a lot about pump storage hydro, but of course, conventional hydro can be a form of storage as well, because we've got reservoirs, and non-production can be a form of storage itself, where we simply shut the machines, hold, and then produce later. So there have been some reports recently by the IEA on hydro, including conventional hydro's participation to storage. But for the rest of this presentation, I'm really going to talk to you about pumped hydro. The real message on this slide really is to say that in every continent, we can see an increase in the amount of renewables. And basically, therefore, this challenge is truly a worldwide challenge. If I now go into a little bit more detail about the technology, and it's often said that pumped storage has been around for decades, and it has, but there's a lot going on. And I'd just like to continue on the sort of history and then bring you up to date. So we saw that a lot of the fleet that's currently working was put down to accompany thermal and nuclear power stations. And the technology that's still being used today that is behind that is known as reversible pump turbines. Basically a machine that can work in both directions, can turbine or pump. And that's the sort of bedrock technology that we've had for about 50 years now. In the 1980s, all the way up to the 2000s, those power plants were basically linked to nuclear and linked to coal power plants, and were essentially pumping in the nighttime when there was excess energy, and then turbining typically twice a day for the morning peak and then for the evening peak. So the number of starts and stops was relatively limited. It was a very stable operating rhythm. And the main accent that we put on development was really to have the highest possible efficiencies for the best possible revenue from arbitrage, buying cheap and selling expensive. That model has now died, or it's in the process of dying. And there's a crack that I tried to put on this slide to show that what was good for the 1980s is no longer suitable for the 2020s. And in fact, we talk a lot about the energy transition, and I could even give you a date, as far as I'm concerned, as to when the energy transition truly started to happen. And it's linked to the US. For me, it basically happened in 2016, 2017, because until that date, all that big fleet of pump storage in the US that we've spoken about before, that was synchronized with nuclear and it was synchronized with thermal. It was pumping in the night and it was producing in the day. What happened in 2016, 2017, that reversed. Pump storage is now pumping the majority of the time in the day and turbining in the evening and potentially at night. So that link with thermal nuclear has broken, and the new link is with renewables. So it's not just talk about the transition happened in the US for the pump storage fleet in 2016, 2017. And I'll show a slide on that in a moment. Another key thing that has changed is that our customers are no longer just looking for efficiency. They're looking especially for flexibility and reliability and longevity. And these were the points that were raised earlier as well. We're really looking for assets to be as adaptable as possible, as quick changing as possible, as reversible as possible, and as cyclable as possible. Now, sorry, that's a terrible use of the language. But cycling is something that we see increasing more and more, both in terms of new build. Our customers are specifying that we need to be able to do starts and stops 6 to 10 to 15 times per day, whilst maintaining a 50-year machine design life. And this is something that you can see as something of a paradox, because there are other technologies which are able to bring a significant contribution to the transition, but are very difficult to cycle. In the pumped hydro space, we're seeing a strong inflation in the number of starts and stops and the number of cycles that we're being asked to design for, and with the existing fleet to actually improve and reinforce the existing fleet so that it can take that cycling into account. So we've put a lot of emphasis on lifetime cycling. You can also see on the right-hand side of this slide, a lot's being done as well on ramp rates, reactivity. You can see the graph where basically we're always trying to go faster from for a start to get onto the grid, to also do a fast transition between the operating modes, for example, between pumping and turbining. I'll mention that in a moment. We're also trying to get a wider operating range for the equipment, either new equipment or existing equipment. And one of the latest technology developments is variable speed, which basically gives us another degree of freedom with which to be able to bring more flexibility to units. And in particular, it allows us to modulate or to regulate the power absorbed in pumping mode, which isn't possible with a fixed speed machine. So a lot of technology has been put into faster reactions, wider operating ranges, variable speed. So there's a lot going on in the technology space for pumped hydro. I'll just pause for breath. That really is my main slide to talk to you about technology and how the technology that's being developed can help integrate and aid the energy transition. If I then just give you another slide, this is a slide coming from California, the Helms pump storage facility, which is about a 1.2 gigawatt facility in California, which was built originally to accompany Diablo Canyon, a nuclear power plant of roughly twice the size in terms of power. And basically, I just wanted to show this. This is coming from the data from the power plant itself, but it's just to back up what I was saying to you before. Basically, we can see the nighttime pumping is shown in turquoise, light blue, and the daylight pumping is shown in dark blue. So it's basically just illustrating to you what I said verbally a moment ago. We can see on this power plant, of course, located in California, which is where a lot of the transition is going on, or it's an early mover, let's say, as far as the transition is concerned. We see that change. And the hydro is accompanying, let's say, that change. Two other case studies just to bring out the technology. One coming from Israel. Israel's very interesting in that it's an electrical island, even if it's not a geographical island. They have no interconnections with the neighbors. They'll have no help from the neighbors if their transition from fossil fuels to, for example, solar fails and they have a problem with the grid. So they need to be autonomous. It's a very water scarce country. They basically had no hydro a couple of years ago. But in order to decarbonize an 18 gigawatt electrical grid and go towards more solar and concentrated solar, they took the decision that they would need 800 megawatts of pump storage with approximately 10 hours of storage each time. And really they put a premium on reactivity. So these are the machines, for example, that the customer wants to be able to start in less than a minute. They want them to be able to switch from pumping, for example, minus 150 megawatts to full generation plus 150 megawatts in less than 90 seconds. Those are the kind of constraints that we're now getting. I think it's very interesting to note that we actually went beyond those requirements. There were bonuses to go even faster. So they're basically being paid for speed, and they were prepared to pay the equipment manufacturers as well for speed. So those machines actually can start and get to full power, or they can switch from full pumping to full power in less than a minute. Now, I know that less than a minute is not very fast as far as batteries are concerned, and batteries, of course, have a role to play for very quick reactions. But when you look at this kind of industrial size machinery, switching from minus 150 megawatts and then turning in the other direction and producing 150 megawatts in less than 60 seconds is quite an achievement. So you can see that's one case, flexibility of new technology that didn't exist 5-10 years ago. No need for fast reactions when you're simply paired with a nuclear power plant and you know that day in, day out, you've got more or less the same schedule. Another item I'll just mention then is variable speed. An example coming from Switzerland. where they basically said, we've got a lot of water, we've got mountains, let's use them to become the battery of Europe. And in order to have the most flexibility that they possibly could, particularly to go well with wind in Germany, it was decided to use variable speed, which gives a wider operating range and especially the regulation in pump mode. So I've tried to give you a quick tour of the world, a tour of the technology, a tour of what's going on elsewhere. If I just bring it back now to the US, I know there were some comments earlier about pump storage and future pump storage. So there is an existing fleet, which is significant, which is contributing a lot already to the transition. If you remember back, I said 23 gigawatts of installed capacity. This is actually a chart coming from January of last year, so it's not been updated yet for 2022. But we can see that there are already 38 gigawatts of plants which have got FERC permits. And there's approximately another 35 gigawatts which is going through the process. So you can see that even if all those projects don't come to fruition, there is the potential to double or even triple the US fleet in power terms. And those are real projects going on right now. I think it's interesting to see the map because you can also see the distribution, particularly, for example, in the western side of the US. So I got to my last slide. Really, it's just to emphasize that pumped hydro has a significant fleet in the US, is already a significant contributor. It can bring more. We can bring new capacity, and there's a lot of new things going on in terms of technology. We've already had a chat with a couple of people. There is a report as well that you might find interesting. Some details are shown on this slide. Otherwise, you can see the link in the chat where we were looking at the value of pump storage with high intermittent renewables when we're getting to 30 or 50% penetration of wind and solar. So I've talked a lot. I've talked a little bit fast. I hope you managed to follow me okay, but I've kept just to the time. So I hope you found that interesting, and I will be more than happy to answer any questions later. Thank you.
Thank you, David. Yeah, great presentation, and a good reminder that when we're working on technologies, the other technologies are not standing still. So you have to be mindful of what the competing technologies are doing in a space if you expect to be into that space in the future years. Okay, we'll transition over to Dr. Tsay. So Yi Tsay is the director for the Precourt Institute of Energy and a professor of materials science and engineering at Stanford University. He studies fundamentals and applications of nanomaterials and develops tools for their understanding, specializing in energy and environment-related research, and is the Fortuné Founders Professor of Materials Science and Engineering at Stanford University. Professor Tsay holds a lot of prestigious titles, including being a member of Stanford's SLAC National Accelerator Laboratory. He's a fellow of the American Association for the Advancement of Science, Materials Research Society, Electrochemical Society, and the Royal Society of Chemistry. He obtained his bachelorate in chemistry and from the University of Science and Technology of China, and his PhD in physical chemistry at Harvard University in 2002. So without any further ado, I'll turn it over to you.
Well, Craig, thank you for the very nice introduction. So it was great hearing about David's talk on pumped hydro, one of my favorite energy storage technology. Well, David, I'm going to speak about batteries. I couldn't speak about pumped hydro. I'm no expert on that. So I work on batteries for a number of years right now. Sharing with everybody about some of the perspective. It's more important it's during the discussion session. So, well, let me come back to this plot of this schematics of solar and wind. The electricity cost is so low. So what we need, right, for the grid scale for really integrating solar and wind into electricity is this multi-time scale of storage. early in the the early talks, Sarah Kurtz, for example, mentioned about that as well. So we look at this from minutes to hour to day to week to month to seasonal. And their requirements are very different. And first thing I want to emphasize is the scaling is, let me just use 4-hour storage, assuming we are going to do 100%. Fast forward to 2050, 100% clean electricity require at least 4-hour storage. It actually requires much longer duration, for example, to seasonal. So we are talking about 10 terawatt-hour of batteries. If batteries is the other choices of storage. So this is gigantic market right here, assuming $100 a system level cost in the future and per kilowatt hour, this is $1 trillion market. So scaling is very important to have these gigantic batteries to work out. Well, now, if you look at different time scale, what's the cost requirement right there? I mean, this is a rough number, right? 4 hours, ideally we want somewhere about $200, $300 per kilowatt hour. Lithium ion can already do that and the system level cost. A day, we need 100, a week, 50, month, 20, seasonal, less than 5. So the cost requirement becomes more and more, the longer duration you need, because of the number of times of cycles you can do becomes much less. So your capital cost of the storage needs to go down. So that's one perspective. The second one is, let me emphasize the life, both calendar life and cycle lives. Lithium ion, about 10 years or so. So the life is so important. At the end, the levelized cost of your system, right? Both the years and also the cycle life, is the capital cost divided by your cycle number. Certainly, there's also energy efficiency consideration right there into the equation. And also a longer life means the number of times required to go back to recycle your technology becomes less. That's so important as well. And the next is maintenance free in all climates, extreme cold or heat, right? Solar and wind. Solar often is in a very hot weather, and wind it's often in the cold weather right there. And we look at current lithium ion, the temperature operation window is very narrow. That's why you need to build air conditioning actually to control the temperature of lithium ion. Also, remember, energy efficiency needs to be high. I didn't see too much emphasis yet, right, in the earlier discussion. I touched upon a little bit. Well, every time we talk to industry, energy efficiency number comes up as very important as a choice of the parameter. If energy efficiency below certain value, just not interesting to industry at all. So this needs to be into the discussion. How high is high, right? So we need to be very safe. I use the lithium ion battery as an example. There's so many accidents recently in the last few years for the grid scale stationary storage, and that cannot be overlooked. Cradle to cradle recyclability, this comes back to the scaling problem. Once the scale is so big, you absolutely need to think about how do you do reuse and recycling. So the benchmark lithium ion, I use the cell level number right here and the cost kilowatt hour 100 to 120. This number actually goes up this year, since last year actually, because there's so much demand from the electrical transportation. All these raw materials really go up. The cost of lithium ion, instead of going down in the past 1 year, is actually going up. So we do need to think about, if it's the batteries, what type of battery technologies we need to invent or reinvent in order to get to the grid scale. Let me share with you a few examples, some of the thinking. So over the past 15 years, my lab worked on, for example, Prussian blue type of materials. Energy density is not high, it's low, but it's very high power. And we look into membrane-free lithium polysulfide flow batteries. And we also recently looked into hydrogen gas batteries. It's not fuel cells, batteries. A new type of molten lithium metal batteries right there. So we are learning quite a bit and use the criteria I outlined in the previous slide. So maybe let me share with you this one particular example. I see this, it's very, very promising, is on the metal hydrogen gas batteries. So this is the batteries using cathode is nickel hydroxide, become oxyhydroxide. Anode is basically half of the fuel cell is hydrogen, become water back and forth using catalyst, right? The full cell reaction is written the following: nickel hydroxide become oxyhydroxide during charge and generate hydrogen. This is inside a tank, right? And you say, well, why this is exciting? Well, coming back to the lifetime question, how many years, how many cycles your batteries can do? And if you look at the more than 150 years of human, electrochemistry history, and say, what's the longest lifetime chemistry ever invented by human being? And one of the choices is actually hydrogen become water. This is highly reversible, virtually infinite number of lifetime. What's the choice of cathode then on the positive electrode? It's actually nickel hydroxide become oxyhydroxide, 100,000 cycles demonstrated. So can you combine these two to construct a battery? So this is called nickel hydrogen gas batteries. So we showed that, and back in 2018, published this paper, right? This catalyst is nickel moly, cobalt. So it's working so well. After we invented this, we kind of searched the literature and found, oh, this chemistry has been used actually by NASA. And so is, the Hubble telescope for more than 30 years now. So zero problem, very safe, billions of hours of, experience. It's 100% mission success. But for aerospace application like this, the cost was too high. It's because it used a platinum as catalyst. Now we changed to a nickel moly. The cost is reduced on the catalyst side, right? 10,000 times around that neighborhood. So now we can make the cost very low. So let me share with you, using electron deposition, we produce this anode catalyst. So I won't go into details of that in 3-dimensional electron, and really start to see, well, these a cell, they are very stable. Let me just quickly jump to, for example, this cell is not small. It's actually in the lab, in university lab already more than 500 milliamp hour cycle for 600 cycle. We showed that this can run 10,000 cycles. After that is 95% capacity retention. So extremely exciting to see this. Remember, this battery has very long shelf life, the calendar life, and this has been demonstrated in the legacy nickel hydrogen cell. This now we start to see also working with the new catalyst. So not only the nickel hydrogen, this can go down to the past. What's the possible cathode? Can we consider manganese, lead, and iron, right? This has the metal cost per kilogram is about an order's magnitude less than nickel. This will offer you an even lower cost chemistry, right? They potentially allow you to get to the seasonal storage. Remember the number we are looking into, kind of $5 per kilowatt hour. You really need to have very low cost, highly abundant materials for doing that. So we actually invented this manganese chemistry as an example, manganese dissolution and deposition chemistry as cathode. Without iron selective membrane, your manganese 2+ can actually mix together with anode. It won't affect your anode catalyst. And we show in this Nature Energy paper back in 2018, actually very exciting. So around very long cycle life, 10,000 cycles. And certainly this now is at a time we need to, how do we bring this out to the industry? Well, let me share with you a startup company I founded in Navania. So 3 months ago, we announced we raised Series A, $125 million Series A. To commercialize our metal hydrogen gas batteries, very long life, 30 years, 30,000 cycle. 0 accidents. People say, well, you have hydrogen in there. How can it be safe? This is still in the container. We have done a lot of safety testing. You can burn these batteries in a fire. You could use a bullet to shoot on this battery. We have been testing that. It's very, very safe, and nothing happened. So it's flexible from minutes to minutes. You can have high power to 72 hours. And for the nickel hydrogen case, like 72 hours, it's already great. Seasonal nickel's cost is not high enough yet to realize that purpose, but manganese will do. 0 maintenance, and its operating temperature is -40 to +60 degrees C. It's just amazing. This is aqueous solution, a basic solution chemistry. Going down to -40 degrees Celsius, it does not freeze yet, because of the strong base in there. Innovative is at this moment put out this inner station, deliver 10 megawatt-hour this year, will be a 100 megawatt-hour next year of storage. So this, I want to give you an example, but let me now come to for today's purpose, also brainstorming some of the important points right here. We are seeing the electrical transportation is taking off. And there's a billion passenger cars on the road, assuming 50 kilowatt-hour per car. So this is 50 terawatt-hour batteries right there, right? So building up, we will see a big fraction of that will start to show up in the next 10 years. So vehicles to grid integration got to be important. How do we utilize the install capacity installed inside the car to serve for the purpose of the grid? This requires us how to use data. How do you do the a trading between the car electricity and the grid? I mean, this is this discussion needs to be going, because cars are parked there most of the time, not utilizing the battery's capacity. If you use the shallow charging, discharging, right, I will just say from 10% to 30-40% range, utilize lithium-ion batteries. The life of lithium-ion batteries can entirely support the case used for the electrical grid. So how do we do that? So could be exciting. So let me summarize for conversation on the energy storage, right? So the storage technology over different time duration got to be important. The scaling issue on many terawatt-hour or possibility got to be important. Energy efficiency, what's that number? Depending on the use case, right? And people talk about, well, many people say I at least need to have 70% for the batteries, otherwise it will be too low. That's why an electrolyzer coming into equation. We need to discuss about energy efficiency. Electrolyzer and fuel cell, what's we use depending on the use case right there. Cost, of course, continue to be important depending on the time scale, the duration. Flexibility and all type of climate at different locations, recyclability, safety, and also remember we got to leverage the existing industry. And we look at the solar industries, silicon has been dominating. Silicon has been leveraging the semiconductor industry. Lithium-ion battery industry for electrical transportation, leveraging consumer electronics. This just keep building up the force, innovation force, and the cost reduction due to the scaling of existing industry cannot be overlooked. How do we use transportation electrification combined with grid? My previous slide, I believe, is also important. Well, as last slide, let me advertise, right, to impact in the energy storage, considering the future energy system. What Stanford Energy has organized our activity together in the past 20 years under Preco Institute of Energy. So Bits and Watts Initiative, Storage X Initiative, actually directly linked together with what today's discussion topic is. And we are launching Hydrogen Initiative in May. And there will be a carbon removal and sustainable manufacturing initiative as well. And we also have been looking into sustainable finance and policy and so on. I think with that, I should just stop right here. Look forward to the discussion. Thank you.
Thank you, Dr. Tsai. And I want to commend our speakers. I think everyone is staying right on time, so that's always nice. I think the audience appreciates a session that stays on time. I would also like to encourage the audience to post questions in the Q&A box of the Zoom meeting. We've got one more speaker and then we'll head into the panel discussion. And if we have some of those questions queued up, that'll help us. And it also gives the panelists the opportunity to look at those questions a little bit before time and consider their response. So with that, we will transition to our final speaker before the panel session. That's Dr. Ben Bollinger, who's the Vice President of Strategic Initiatives with Malta, Inc. Dr. Bollinger leads strategic initiatives at Malta, which is a venture-funded long-duration energy storage startup company that's developing a 100 megawatt and 10-hour pumped heat energy storage system. Ben has worked in this technology space since 2007 when he co-founded a company that developed isothermal compressed air energy storage. We heard a little bit about air energy storage earlier. His background is in systems engineering and multi-domain system modeling. And Ben received his PhD in engineering sciences from the Thayer School of Engineering at Dartmouth. So thanks for joining us today, Ben, and look forward to your presentation.
Thanks, Greg. I appreciate it. Put my screen up here, which is hopefully showing.
Yep, we're good.
Is that the presenter mode or is that just the screen?
No, you're in the presenter mode. You look good.
I want to touch on something a little bit different today, and that is kind of zooming out to the grid scale and looking at integration of energy storage into the electricity grid at very large scales. So if we look at power generation growth over the past 20 years, almost the entirety of the growth in power generation has been in natural gas and has been in renewable energy, and specifically intermittent wind and solar as the growth areas. And this has caused an unprecedented change in how the grid reacts to balance supply and demand across not just timescales, but across geographies as well. So if we look at some of that trend, we are moving from a balancing scenario where intermittent renewables are trading off with natural gas providing power at nighttime and lithium-ion batteries picking up the peaks, to a scenario 10 or more years out in the future coming where the amount of renewables on the grid are going to be substantially higher, and storage is going to come in and fill that gap and do that energy shifting. So I've been told to never put equations in a presentation, but in this case, I think it actually kind of helps walk through the challenge at the different scales. And really, this is balancing supply and demand, which is what the electric utility space has been doing for the last over 100 years. And this equation is changing. So the demand from our economy and our factories and our homes, and now increasingly our automobiles, needs to match and get paired with all the different generation sources. And those are typically set in non-dispatchable generation, such as classic nuclear and combined heat and power installations, along with what is kind of the bulk of the power generation fleet today, which is coal plants, natural gas plants, and hydroelectricity. And now increasingly for the last 20 years, intermittent electricity generation. So all of these aspects balance with then that remainder, which is net electricity imports. And this is important because this equation needs to be balanced across a certain balancing region, which is a fixed geography. And every geography needs to make this happen. So when we look at these electricity imports in a little bit more detail, there's a paradigm shift here happening as well. So if we think all the way back to Hurricane Katrina 20 years ago, linemen came from all over the country, California, Maine, the Midwest, to help bring New Orleans and the surrounding area back from what was a severe disaster. This aspect of borrowing from our neighbors to multiply resources has been how the US has done disaster response for a very long time. And that has worked really well for a very long time. What we're seeing now is a scenario where we have common cause failure. 2 years ago, in the spring of 2020, when coronavirus hit, we were in a situation where states and regulatory areas were not able to pull from their neighbors because their neighbors were facing the same problems and were facing the same shortfalls. And as a result, everybody was left scrambling for resources that they didn't have because they couldn't leverage their neighbors for that peak. And we're now seeing this kind of a scenario in electricity markets as well. If we think back to California a year and a half ago, for a number of different reasons, California was short on power generation in August of 2020. And the hope was to pull in from their neighbors to import that electricity and balance as they typically do. And those imports didn't happen because of various issues with their neighbors as well. And so California was left with rolling blackouts. And then of course, there are areas where it's just not possible to leverage your neighbors because the physical interconnections are not there. Texas is a great example in ERCOT. David Havard called out Israel earlier this hour as another example of an energy island that cannot leverage its neighbors. So when we look at trying to balance this equation, the idea of being able to do that through net electricity imports from one's neighbors, I would say is questionable in terms of future reliability. And I think this is an aspect that utilities and balancing authority regions in particular are starting to think about and to address. So how do we then do this as our electricity demand becomes more and more peaky with the increased number of additional electrical appliance and transportation that is on the grid, but at the same time, our number of dispatchable electricity generators in the form of coal plants in particular, but also some gas plants are retiring, and the intermittent generation sources are increasing. And the solution, of course, is not having to balance that exactly, but storing it instead. Having electricity as a commodity have storage, just like every other commodity does. And in this case, net energy storage can replace the functionality that previously was met with gas plants and with imports from one's neighbors. So then how fast and how long? And this is a question that a number of folks today have touched on. You know, this equation needs to be true at every time scale. It needs to be true minute by minute, hour by hour, day to night, week to week, and season to season. And that is our challenge as we move forward with the energy transition. So this kind of brings us to where we are today in that energy transition that has started and is increasing in pace. You know, if we think about variability on the grid and resilience, you know, the solution of yesterday was gas peaker plants and batteries for quick peaking. And the gas plants in particular provided load following to match the demand with the supply. And they also provided frequency support in the form of physical spinning inertia on the grid and resilience to the grid as well. When we look to the future, where the energy piece comes from intermittent wind and solar, that energy piece at low cost is fully served by wind and solar, but it needs to be balanced with some resource to provide the load following and the frequency support and the resilience to the grid. And that is where long duration energy storage really comes into play, that can fill in those other services that had been provided by the retiring fossil assets that are there. And my company's solution, Pumped Heat Energy Storage, is one of many out there on the market today that can fill that space and enable renewables to continue to be deployed at rapid pace without running into grid stability or balancing issues. So a little bit about the company. When we say long duration energy storage, we mean in this 8-hour to 200-hour range, and the specific needed duration is really application specific. And we are working at grid scale, 100+ size plants, leveraging partnerships and existing equipment that are on the grid in order to put grid scale energy storage out there in the market today. So in terms of how it works, it's effectively a heat pump and a heat engine combined with thermal storage tanks. So just like any refrigerator or mini split heat pump unit, the Malta power unit moves heat from a cold reservoir to a hot reservoir. In this case, the hot reservoir is the high temperature molten nitrate salt tanks that are and have been commercially used in concentrated solar plants for the past 10 or 11 years. And then on the power generation side, the power unit is a heat engine, very similar to any thermal power plant today, either the modern steam cycle plant that's shown with the blue and orange there, or even older 70-year-old power plants or plants that existed 70, 80 years ago that were the same open air or a closed air Brayton cycle that the Malta plant uses. So the idea of combining a Brayton cycle heat pump and a Brayton cycle heat engine with liquid thermal energy storage, hot and cold, is not new. The idea was really argued over 10 years ago by Professor Laughlin at Stanford University. And his argument was that this is the necessary, sufficient, and doable means for enabling low-cost energy storage for the electricity grid. And since the inception of Malta Inc. 3 years ago, we've really taken this mantra of necessary, sufficient, and doable and focused on execution of this idea as a commercial energy storage technology. And a big piece of that execution is really the formation of large scale partnerships with both OEMs and end users to enable us to not do everything ourselves, like many startups try to do, but really leverage the decades and sometimes centuries of experience that these partners bring to the table so that we understand and correctly allocate the risk across projects so that we can make projects commercially financeable and put in the ground. This is true across all of our development efforts and really falls on the execution side into the intersection of technology and economics and the policy space that really allows the projects to have the revenue certainty that they need to move forward. So to that end, Malta as a company is very actively involved in the regulatory space, both in the US and Canada, as well as in Europe and across the world, looking to make sure that long duration energy storage has a seat at the table along with batteries and other approaches for enabling the energy transition to 100% renewables. And as we have worked on this, and the industry as a whole has worked on this, the use cases for long duration storage are becoming clearer, and the revenue stacking capabilities are becoming clearer. Some items that really stand out, especially in the US, is the growing chorus around repurposing of retiring coal plants into thermal energy storage plants and leveraging the locations, the interconnections, the availability of transmission for those plants, and leveraging the skilled workforces and the communities and really keeping those communities and workforces alive as the plants transition rather than having those plants close and entirely go away. Co-optimizing energy storage with gas peaker plants to improve operation and in net reduce emissions is another short-term opportunity that has value in a number of different markets. Combining and integrating the large-scale energy storage piece with industrial decarbonation is another use case that is really becoming clear in a lot of applications. This applies to not just district heating for clean green heat to district heating areas, which do exist in the US, although not as much as in Europe, but also to lumber and wallboard manufacturing and other industrial uses of low-grade industrial heat. And technologies like the Malta system that can provide 120 degrees C output heat at large megawatts thermal as a byproduct of the electricity storage process really has that opportunity to pair in the correct location to make green one of the harder industries to make green. And finally, of course, firming of renewables is kind of one of the key pillar example use cases for long duration storage. And this really is done and is being looked at a number of different levels. This is being looked at both at the project level, behind the fence, if you will, of a hybridized solar PV plus thermal energy storage style project, but it's also being looked at a portfolio level across a utilities regional portfolio, and also at a larger balancing authority region area in terms of the energy storage that's needed across the various different markets, which are significantly different from one to another. So, a parting thought in terms of how much storage do we need and where do we need it? There have been a lot of numbers that have been put up on the screen that have started with a giga or a tera in terms of the number of watt hours of storage that are used. And in balancing this equation and looking at individual size projects, there are many, many opportunities for distributed energy resource projects across the country at very large volumes in local communities. There are also a number of opportunities for very large scale projects connected to transmission. If we look at some of the low cost renewables that are coming on the grid today worldwide, these are not small projects. Costs are being driven down to PPA prices that are a cent per kilowatt hour or close to it. And at those prices, the size and the economics of a project really are the key drivers. And in the limit where that charging cost goes down towards zero, round trip efficiency, for example, becomes a moot point. But the key driver is these projects are gigawatt scale projects, and gigawatt scale solar and wind require gigawatt scale storage in order to be integrated locally at that site. So one way that we can do this and one way that we can focus on this in the near term is looking at the resources and the infrastructure that we have in place. The transmission grid across the US is coincident with the large scale generation assets that we have utilized over the last 40 to 60 years. And many of those plants are in the process of retiring or retiring soon. And not only not providing their energy, but also no longer providing their load following and their grid support and resilient services. Taking those plants and leveraging the interconnection and the transmission that's there and repurposing them as thermal energy storage assets is a way that we can add in the storage that we need into the grid to enable the continued deployment of renewables in a way that makes sense, both from an economics perspective, as well as from a community resilience and a technology perspective. So that's really our goal at Malta, is to enable the continued pace and acceleration of the deployment of renewables into the electricity grid, and decarbonize not just electricity, but also other sectors as well as the opportunity arises, by providing that grid stability and load following capability that the long duration energy storage of physical spinning systems can provide.
Thanks, Ben. All right, so we are going to transition now to the panel period, and I'll ask our various speakers to put themselves back on screen so we can see everyone. The audience, we're asking to, if you've got questions, please post them in the Q&A box, which is below your screen. You might have to mouse over it to get that to appear, and we'll take as many of those as we can. I'm going to begin by posing a general question, and we've had speakers in different areas. So we've had David talk about pumped hydro, Yi talked about battery technologies more broadly, Ben talked about pumped heat energy storage, and Jean talked about hydrogen, and Sarah kind of gave an overview of everything. So for those different technology spaces, I wanted to ask you about hybridization, and several of you talked about this a little bit in your presentations. So what do you see for your technology space as being the most advantageous opportunities for hybridizing, either with the electricity generators or users or other storage technologies? So things that might be advantageous for early adoption of your particular technology. And I guess I will start, I'll go clockwise maybe in what I'm seeing. So that puts Ben up first. If you want to talk about where you think hybridization with pumped heat energy storage might fall.
I think there's a number of different hybridizing opportunities. I do think that each one of them comes with questions as well. For us, an obvious hybrid is in the industrial heat space. Providing both power and heat into a town that has a district heating system is a great way to hybridize. The question there, of course, is which drives dispatching, the heat or the electricity, and how is that most optimally done, and can the contracting be made to work out for that? Another way of hybridizing is across all of the different value stacks and the stakeholders that are in there. So in certain markets, where generation and transmission are owned and controlled by different entities, the value that storage can bring spans multiple stakeholders. So an energy shifting value is received by the local utility that controls power generation, but the grid stabilizing effect and the short circuit current that it can provide is that benefit is received by the transmission entity. So how do projects integrate those different stakeholders together so that each of those value adders can be integrated into one set of project economics? And that's really a policy question moving forward. And those kinds of policy issues, I think, are a forefront of energy storage development and integration.
Thanks, Ben. So on my screen, I see David next if I'm going clockwise. So David, from the pumped hydro sector, where do you think your major opportunities are?
Okay, it's not easy for me to say in that there's a lot of movement, or I would just say early movement, early adopters, but they're only at a relatively limited level for now. If I give you some examples, if I just talk first of all about conventional hydro, there is a massive facility in China which has a solar farm and a hydro plant, which are very close to one another and which have a joint control. There is also a pump storage facility in Germany which has put a limited amount of batteries so that they've got a very fast reaction for the frequency response. There are a couple of places, and we're actually working on right now, hybridizing batteries with hydro, with pump storage. There's a customer in Portugal looking to do floating PV on the reservoir, plus batteries, plus pump storage. But I would say at the moment, they're all starting only, and it's difficult. Sorry, another one is Hydro-Quebec has recently announced they're going to produce hydrogen. I think that was an announcement in the last couple of days. They're going to produce hydrogen using the hydro from Quebec province. So it's difficult, I would say, to say where it would go. For pump storage hydro, if we stay in that sort of space that we talked about at the beginning, maybe it's combining with batteries to have the short bursts of power. But to be honest, I think it's a little bit early to say.
Mhm. Thank you, David. Okay, around the circle then, Yi is next up. Now you covered a lot of different battery technologies, and I'm callously lumping them all together as batteries. But where do you see where they may be hybridized with other technologies or other users?
So Craig, let me mention maybe hybridizing from a few perspectives. Well, if you look at the batteries for the short time scale, from minutes to about, I would say, a couple of days, 3 days, within a week, this might be the batteries domain. The longer time duration it is, it's harder for the batteries for the cost reason consideration, right? So just among the batteries technology itself, the first perspective is this lithium ion and others, this hybridization within the batteries domain, you can see that already. And also, let me paraphrase Sarah's terminology of cross-sector, right? Cross-sector is transportation, electrical transportation versus the grid. Really cross-sector, but build on the batteries technology. That's a hybridization of a use case got to be built up. That second perspective. And then now consider hybridizing battery with other technology. Potentially hydrogen is a good one. Well, Ben talked about the thermal one. I can see that pump hydro as well, David's domain, and it's very clear. It's different time scale of utilizing the benefit of each technology's strength. So there's a lot of hybridization that can be done together. So I'll pause right here.
Okay, thank you, Yi. And then Jean, on the hydrogen side, same question. Where do you see the primary opportunities there?
I see a big opportunity for centralized electrolyzers that load balance the grid and also are driven by renewable electricity to make the power. And I also see hybrid systems that are made from commercial off-the-shelf technologies with research technologies. So it's a different perspective, but it's about getting your products off the shelf or having to design, engineer, and assemble on site. Thank you.
Okay, thank you, Jean. All right, before we take it, we got a question that was directed toward Ben, if you want to check that one out in the Q&A, Ben. But I want to give Sarah and Nate an opportunity to comment on the question of hybridization.
So maybe I can talk at a very high level. In general, looking at the principles behind where we're going with hybridization. I think hybridization is going to be very important. It gives us innovation to how to improve the system. However, if every system we do has to be specially engineered, it's not going to be cost effective. So we're going to need to look for those applications that can be deployed multiple times, multiple ways, and to think about them in different categories. Then one is the first one would be when you can provide base load power then. And that will simplify a lot of the contracts, and the utilities are obviously going to like to have a system that can just provide flat output. And if you can come up with a way of doing that, which is difficult, but if you can, there will be value in that. The second is to have a hybrid system that can be dispatchable to be able to respond to the load as you're going. And that will be actually more valuable to the grid, but is actually even more difficult than doing the the base load, depending upon what your resources are. Then the third to look at is that I do see that there are a lot of opportunities with the cross-sector hybridization. And I think Jean hit the nail on the head pointing out the electrolyzer one. And I would add to what she said, according to our calculations, and I kind of skipped over that slide, but what you'll be looking at is that to make the electrolyzers be appropriate and effective, you'll need to combine them, say, with a solar system plus batteries or some form of storage that gets you through the night so that you can run the electrolyzers off of the solar system during the day, off of the storage at night, and then turn them off in the winter when the solar isn't coming. It works easier for the electrolyzers paired with wind. You can get to a high enough capacity factor that you may not need to have a battery or some form of storage to keep the electrolyzer going when the wind dies. But there's certainly lots of things, and I apologize. I know that we've been asked to talk about hybridization in our talks, and I didn't get to that.
Not a problem. Nate, did you want to comment on hybridization?
Sure. I think say two things, and maybe a lot of people in the audience know this. Right now, there's a lot of batteries being deployed with solar PV plants in particular, and we think that a lot of that is driven by the current tax credit structure. So it'll be really interesting to see, depending on how various bills in Congress roll out, whether there ends up being a tax credit for standalone storage and what that does to the marketplace in terms of driving hybridization or reducing hybridization with solar PV. And I think that's interesting. I think in a, from a grid operator's perspective, if the grid operation is efficient and world-class, you do not need to co-locate the generation and the standalone storage. There is some value perhaps to acceleration, where we see that people who have an existing interconnect for perhaps a large wind farm of say 300 megawatts, that they can push more power through that if they hybridize wind, the existing wind, with co-located PV and co-located storage. So they're not exceeding their interconnection limit, but they are still pushing more kilowatt hours through that limit. And so you're seeing some of that hybridization on top of existing plants that are out there, because it short circuits the need for additional utility approval, which I think is part of what's going on in the marketplace.
Yeah, as an engineer, we think of the hybridization challenges technically. I think Ben's point about the business relationships is going to be equally challenging in terms of how you each, realize value when you've got multiple entities trying to play for facilities, for example, that may not be co-located. So there was a question in the chat, Ben, and I think you've already worked on that, but I would like to circulate back to that for the wider audience. So I'll read the question. If you're comfortable just going through your response, that would be great. So Malta has talked to the Hawaii Office of Energy regarding their Powering Past Coal initiative that will close one of the last remaining coal plants belonging to HECO. That's the power company in Hawaii that serves roughly 20% of Oahu's load later this year. As of now, Hawaii and HECO do not have a clean replacement established to meet this schedule. So is this something that Malta's technology would be applicable for?
It could be. I need to look at that in more detail. We have looked at Hawaii in the past, and I think in general, the smaller grid areas are more interesting from an islanding perspective. And it's in the smaller grid areas where the need for long duration storage in particular is the largest. Hawaii has been doing hybrid projects for a long time, generally at smaller scale than the 100 megawatt scale systems that Malta builds. But if we look at other areas, Spain is a really good example. It's not an island, but it's constrained in its connection to France. So it's a quasi island. And in Spain, they're at the point where you cannot get a PPA for solar PV to put power on the grid during the day. They are super saturated in solar PV during the day. All the solicitations that are coming out are for load following solar. They call it sundown solar. And all the developers are scrambling to install storage along with their solar PV. And on top of that, they are, I would say, more advanced in recognizing the ancillary benefits, where they now have different interconnection allowance limits for resources that are synchronous versus resources that are not synchronous, so that they can ensure the short circuit current capabilities and the grid stability that they need. So that is really shifting the deployment space in Spain since last July, when that came out, in terms of the solicitations and the bids that are going out. If we look at Great Britain, it's a smaller grid. They had rolling blackouts 2 years ago and started to deploy dedicated RFPs, not just for storage, but also for synchronous inertia for grid stability purposes. So it's all of these smaller interconnection regions that are that they're seeing these problems first. You know, if we look at the US, California has a lot of renewables, but it's part of the Western Interconnect. So when you average California in with Wyoming and all the states in between, the percentage of renewables is still pretty low. It's further behind the renewable deployment space than some other places, but we can look at those other places to see what our future is going to look like.
And I should say, when we have this dialogue, if other members of the panel want to chime in or add to something, please just speak up or raise your hand.
Can I just
Okay.
jump in then on
Oh,
what
sure.
Ben
Go ahead,
said?
David.
I do fully agree with everything that you said, Ben. Very interesting. And as you point out, that Spain and Portugal are at the periphery of the European grid. And all these weaker grids will be the ones that will see these things first. Just for interest, maybe for the audience, have a look at Tasmania as well in Australia, which is approximately 90–95% renewable now. It's a relatively important grid, essentially with wind, hydro, and then a HVDC link to the Australian continent. So I just say it as an example, just to reinforce what Ben said about inertia, synchronous inertia, and so on. What Hydro Tasmania is doing, has got quite a big fleet of hydro units, so synchronous spinning units, no pump storage. They're actually using a lot of those hydro units in synchronous condenser mode. They're not actually producing electricity, they're just having them spinning to give reactive power to absorb the HVDC and the inverter-based wind. But there are ways to do it, and Tasmania is doing it.
Are they getting compensated for that? Because my understanding was Britain was the first one to compensate separately for the inertia, but it sounds like Tasmania must have figured that out as well.
Yeah, they were supposed to be a couple of years ago, but I still don't think they are. So that, again, and this comes down to some of these positive externalities, which are not fully recognized in a market way. And in a way, HydroTas has to keep the lights on. It's part of their remit, so they do, but they don't get paid for the hydro in synchronous condenser mode. And I don't want to talk too much. I'll let other people speak too, but it's very interesting that you mentioned inertia, because even 2 years ago, Ireland and Great Britain said, we don't need inertia payments. There's no need for it. And now suddenly we're paying for inertia. And I think we're changing the paradigm, as a lot of people have mentioned, and we are going to be inertia poor. And we need to find ways to ensure a transition. Maybe people saying in 2100 we'll have a completely inverter-based grid. Maybe, but we need to get there.
Mm-hmm. So just to follow up on that, so inertia-based systems, I guess I always think of spinning turbines providing that. Does this group have any comment on where that transition lies in terms of moving more to inverter-based power electronics? I'm not knowledgeable in that area.
I'll jump in because I'm not hearing anyone else, but I think the there's research going on about grid stability across very large transmission length using inverter-based resources on either side. And that's an active area of research. I think NREL has some folks that are working on that. I can't remember who. The utility space has solved that grid stability problem across long transmission lengths using synchronous resources. And I think that's the opportunity, is that there are energy storage systems that are synchronous devices, such as pumped heat energy storage, such as pumped storage hydro, that can backfill that capability that gas plants and coal plants have provided in a way that doesn't necessitate the need to have figured that out with inverter-based resources. If we do, that's great. That's an extra toolkit in the basket of the overall utility grid, which the more tools that we have, the better. But I think we do have solutions today. We don't need to have new science be successful in order to make this a stable transition. Sorry, Nate, I think I may have jumped in front of you.
Oh, totally fine. If it's a lot of NREL people on the call, they don't need to hear more from me. But I think I would just add, Craig, that there is a significant effort on what we're calling at NREL the autonomous grid, or synthetic inertia coming from grid forming inverters. And some of that has been around for a while on the mini grid and islanded grid area already. And I think there's a lot of experimentation and data being collected at larger and larger system sizes for those. So I'll see if I can't find a website to drop in the chat here. Thank you.
Okay. So there's a couple more questions in the Q&A right now. I'm going to ask Michael maybe to elaborate on his question. So his question is, do you see ownership issues getting contentious? And I would interpret that maybe it's dealing with some of these hybrid scenarios. But if Michael, if you want to expand on that a little bit, we'll circle back to that one. And then Jen Kurtz is asking, how do you think about reducing risk for deploying these energy storage technologies, especially as our energy system and needs are changing so quickly? So again, the different technologies have different risk factors, perhaps. So maybe I'll start this process again, going the other direction with the technology folks in terms of reducing risk associated with your particular area. So Gene, in the hydrogen side, what do you think are the major efforts that are necessary to reduce risk of hydrogen?
Well, I would say testing out electrolysis using ARES and at NREL to determine in actuality, in practicality, how it all works.
Thank you. I know Jen Kurtz will appreciate that. So for those of you in the audience, Jen is the scientist responsible for a lot of our ARES work at NREL. So let's see, I was going around the circle, so that would take me to Yi if I'm going backwards in the battery space. What do you see as the major risks associated with deploying new battery technologies?
Yeah, maybe this risk, let me just mention one, right? I mean, this risk, this word can mean many things. If I would take a risk right there, I say, well, the safety is a big risk right there. And that needs to be taken care of, particularly lithium ion. Then you say, well, it's a proven technology, you have new technology coming in. A few of them were discussed today. Do you have the track record to be able to deploy for such a long time? You promise, that is 10, 20 years, right? 15 years, 20 years or longer. For the new technology coming in, the lifetime risk is there. And then you say, well, how do you do that? I mean, the bankability, then the rate or your loan, the rate will go higher. There's a way to do it. And the risk question, maybe there's other things. Once there's more discussion coming up, I might be able to mention. So I'll mention these two for now. Yeah.
Okay. Yeah, I think we definitely see that risk associated with it being a new technology in any space. There's always going to be a higher premium applied to that. David, so I also think of this risk question as maybe one related to challenges. And with pumped hydro, I always think of geographic limitations, but what do you see as the highest risks associated with the pumped hydro systems?
The highest risks, to be very frank, are not on the technology side. They're not on the technical side. They are on the commercial side. And if I explain that a little bit, we've got pumped hydro, we mentioned before, it's one of the longest durations. When I say longevity of the installation itself can last for 100 years, the machines for 50 years. So it's a long lifetime, but it's also a long build time. And so the assumptions of today can be invalidated 10 years from now, when typically in the US in particular, it takes 5 years for permits and then 5 years to build. So I think the biggest risk is actually uncertainty and lack of visibility on revenue streams. And I think that could be something that's important for long-term strategy for Malta and for others as well. If the villa bit, you can probably build them much faster than pump storage, but this commercial uncertainty is one of the biggest challenges, in fact, rather than the technical part. If I just mention, it is true, and often people say, what about the geography? You don't have mountains everywhere, you don't have lakes everywhere. There's an interesting study done by the Australian National University about the number of places that where you could potentially do a viable pump storage plant, and there are thousands of them. So you're right to point out that it's not, you cannot just put them where you want, but there are probably more sites out there than people think.
Thank you, David. Ben, you want to comment on the pumped heat energy storage? Major challenge, risks?
I think everything that David said is absolutely true. And I think, there's no one size fits all in terms of geographies and locations. And I absolutely agree that the risk in many cases is not technical, that it is commercial and it is revenue stability side, from a project financing perspective. If we look at, offshore floating wind turbines are proven. Offshore floating platforms are proven. Undersea electrical transmission cables are proven. You combine all three aspects together into an offshore floating wind plant, that's a new first of a kind technology from the perspective of insurability and financeability. And there are forward-leaning insurers that will come in and evaluate the risk and work to support that. But those commercial structures, putting those risk pieces of the puzzle together so that you've got OEM guarantees and warranties standing back to back with an EPC wrap that's going around that from a risk carrying perspective, and having that go face to face with the offtake agreement so that there's no large gap that the insurers are facing from a debt risk perspective. Putting that puzzle together is really the name of the game in terms of getting this done. And the risk in making sure that it's understood, allocated to the party that has the ability to control for it, and then also making the economics work. And that's where things like Bill Gates has spoken about the green premium for new technologies and how there's a higher cost for those first of a kind. That idea is starting to gain traction. And there are now private and public entities that are looking to put tens to hundreds of millions of dollars of funding into new large scale first of a kind projects in order to kickstart them and get them off the ground.
Thanks, Ben. So Michael did clarify that his question about ownership issues, he was thinking about hybrids where you might have different commercial entities involved. So I think this touches on some of the comments that you've already just made. I want to follow a similar trend on this. So we talked about technical issues and commercial issues. What about cultural, societal challenges? I mean, we have seen many situations where we have a technology that we think applies and the money is not an issue, but it's not accepted by the populace for whatever reason. Do you see those as impediments for your technology? And I guess if I'm staying with circles, I'm going to start with Ben again and move clockwise.
I think there's never going to be consensus across the population as a whole in terms of what technology we should do. And I think every solution has a place in the mix of what we're going to need. For Malta specifically, it looks like a power plant. There are some people that are always going to push back against power plants being near, where they live. And it's a technology that enables renewable penetration to increase. So I think, as a whole, I would say I'm not worried about impediments, but it's always on a project by project basis.
Sure. Yes, similarity, familiarness with existing technologies is usually an advantage when we're talking. Yeah. David, with pumped hydro, again, the thing that comes to my mind is just land usage, but are there other issues that you may get pushback for the siting and use of these technologies?
There can be siting or the local population, or for example, some of the big power plants recently put down in Switzerland were in national parks. And so they happened, they were done, but there had to be particular care taken on all the spoil coming from the tunnels and so on to be sure that it was disposed of properly. A lot of pump storage nowadays is underground. So the actual power plants themselves, you don't see them. They're very discreet. Of course, you do see the bodies of water. So that can be a topic in certain places. Nevertheless, I mentioned North Africa and Israel. They're actually using desalinated water from the sea to provide the medium for pump storage. So there are other ways and means to get around things. The final thing I would just say, perhaps, and I don't mean to be overly controversial, but I think there needs to be an adult conversation with people explaining that if we don't do something, there will be more and more blackouts. So what do they prefer?
Mm-hmm. Mm-hmm. Thank you, David. Jean, you want to comment on hydrogen? Do you see any challenges from society, cultural issues with the use of hydrogen?
Yes, I do. Combination of things here. So I talk to a lot of fuel cell electric vehicle drivers who love the vehicle, just love the vehicle and don't want to go back to an internal combustion engine. I talk to city permitters who, given their fire marshal, excuse me, approval of the local safety, they're willing to permit a station. And excuse me, in light of that, I have also seen a number of local people who do not want hydrogen near them. They say, I don't know what it is, but I know I don't want it. So it's a public perception of the value versus the safety versus the economic and environmental impacts. I would say that California's integration of the hydrogen safety panel in station design and in review of operations has been invaluable. And this is the hydrogen safety panel that originated under the PNNL and then moved to IACHE. The panel reviews, excuse me, the design of stations from the point of view of the International Safety Code, which has been adopted by California in terms of wall thickness in the surrounds and proximity to vehicles and truck deliveries, et cetera. So the panel's involvement has done a lot to encourage city permitters to actually approve a site. Also, in the case of SMR facilities, where you have maybe bolt-ons to refineries. There has been a very long process in permitting SMR upgrades. And so that has taken a while. It's getting better, and it has worked, but it took longer than people anticipated. So in summary, the drivers love the vehicles. The cities will permit if the fire marshal says A-OK. And the hydrogen safety panel has done a lot to educate the city permitters and also the suppliers and the OEMs. So outreach and education about safety and how valuable safety measures are and how successful safety measures are is a way to say that overall, systematically, a lot of work can be done to help on the topic of safety, and a lot of work has been done. So I hope going forward, using hydrogen as storage on the grid leverages all those lessons learned and all those case studies.
Yeah, yeah, I agree. Education is clearly a piece of this. The way the education is done seems to be critical. You know, the people have to trust the source of the education materials. They have to be clear that they feel like their voice is being heard. And it's not, you know, it's not a simple process. They have to understand the value to them as well. So stakeholder engagement in general, very important. Go to Yi on the battery side. I think everybody's familiar with batteries in concept, so maybe that's an advantage. Do you see any challenges associated with cultural acceptance of different battery technologies?
So I think maybe compare with the other technologies right here, batteries is a relatively easy one. People have been using, a general public have been using battery from consumer electronics for a long time to now recent electrical vehicles. Batteries, if you look at lithium ion, has this benefit is a modular. I see in the audience one person asking this question is related to that. I mean, it's a standard shipping container, you get a megawatt hour right there. I think people feel comfortable with that. But there's still one question back to what Jean just mentioned, also the safety. If you have a number of shipping containers right there, you know, close to the neighborhood, I can see people will start to say, well, looking at South Korea, there's so many fire incidents recently, so that needs to be taken care of. So Greg, this now come to other battery technology. The nickel hydrogen gas I'm talking about is also modular. It's really, really safe. You know, burning the fire, shooting the bullet. I see the data, very safe. I think those will make people feel comfortable in the neighborhood, right? You know, install those. Lithium ion, because of so many safety incidents, so that needs to be looked at carefully. Then there's other batteries, flow batteries. Can it be modular? It's much harder, you know, and modular. It look more like a chemical plant. I think the social acceptance will be harder when it gets close to the neighborhood. Then there's other type of batteries. I think Forms Energy having this new type of batteries, right? We'll need to see how it looks. I don't have a comment at this moment. This is, I think, depending on the battery's chemistry. Flow will be having a little bit hard time because flow batteries will look like chemical plant. Let's see what other batteries we can. Lead acid is regular, look like usual batteries, but lead acid needs to be careful. People are sensitive towards lead at this moment, right? The lead pollution. So maybe I'll just pause right here.
Yes, yeah. I mean, it is interesting that as people become familiar with the technology, the risks associated sometimes look less than they may be. Lead acid batteries are a good example of that. So let me allow Sarah or Nate, if you want to comment on this question of challenges, particularly challenges that may be non-technical.
I think that it's really a complicated question, as people have been noting. And I tried to think of what would be the number one thing that I would highlight. And what I see currently is that the electric vehicle adoption, for me, it works great. My husband and I don't use our car much. We have an electric car. We have a charger in the garage, so we can just plug it in once a week or something. But there are two key things that I see that are issues. One is that currently, we saw that graph where historically, I think David showed the graph about how the pumped hydro was running at night, and now it's shifting to during the day. But everybody out there it is looking at trying to get people to charge their electric vehicles at night. And if you want to use solar, you need to get them to charge their electric vehicles during the day. So where are you putting in the infrastructure to charge the vehicles? First question is, where are people going to be parking? They've been working at home. They might go back to work. So I think this question, but it also is fascinating to me, having lived in Colorado, parking your car in your garage and plugging it in is like, well, that's pretty easy. In California, nobody uses their garages for their cars. In Colorado, you want to put your car in the garage because if it ices up and you have to spend a half an hour scraping your windshield, it's like, I'm going to get my car in my garage. So you always make sure that you can have a car in your garage. But in California, people put their kitchens in their garage. They run if you go by now, they're doing football parties in their garage. They do not park their cars in their garage. So how on earth are they going to charge their car?
Real estate is too expensive, Sarah, in California. So that's why we utilize the garage.
That's valuable space.
So I see this as a societal issue, and I don't see an easy solution to it. But I do think that we're going to have to figure out, if we think everybody's going to have an electric vehicle, how are they going to charge them? Because so some places in the country, it'll maybe be very easy, but here in California, it turned out to be a much bigger issue than what I had ever dreamed it would be.
Right. And if you don't have a garage, if you're an apartment dweller, or you live in housing that is very dense, that challenge becomes even more difficult.
So moving toward infrastructure that gives you daytime. I mean, my favorite thing, you're talking about like hybrid systems. Why don't all the shopping malls put solar over their parking lots and then give free daytime charging to people, and they can go and shop for 6 hours while they charge their car? Free charging for the shopping centers, I think they'll make a fortune off of it.
I don't know if you're familiar with the Buc-ee's chain of gas resorts in Texas, but these are enormous car transportation truck stops, and they have a mall inside them essentially. And so you go, you fill up your gas on a trip, and then you're expected to shop in the mall for, 45 minutes to an hour. They have streets named after them. They're very large facilities. Nate, did you want to comment?
Yeah, just make a couple of quick comments. One is in our Storage Futures work, we did do work on distributed storage adoption. And I think that'll be interesting, and it'll be interactive with people using their EVs for backup power. And I think we'll see that kind of fear of grid outages, et cetera, driving some additional adoption of some of that bi-directional storage. The other thing I was going to say is that NREL, and I'm sure many others, have a long history with thinking about utility scale renewable energy siting, from bird and bat issues with wind to some of the CSP issues with desert tortoises, et cetera, that Craig, you're familiar with, and so forth. And I think we have done a lot of work there, engaged a lot of stakeholders, and have modified the technology to find a compromise solution, particularly in the face of climate change, which some of these deployments and issues should not be considered in a vacuum, where not doing it will result in other impacts that people need to be cognizant of. So I think that long history is something that we could apply in this area, as well as the rest of the community that's engaged on that front.
To follow up on something there, I think again, from a policy perspective at a distributed resource level, rooftop solar and net metering. Net metering has been a boon for rooftop solar in terms of its proliferation, being able to sell the solar power from your roof that you don't need, and effectively use the grid as a giant battery. And that has increased deployment, but those homeowners are receiving a service that they're not paying for in terms of the grid stabilizing aspect of the grid, being able to sell when you don't need it and being able to buy at nighttime. And I think that's been fine when the levels of deployment are fairly low. It's very akin to electric car drivers not paying the gasoline tax and not funding the roads through the gasoline tax. It's fine when the penetration is low. Those policy areas are going to need to be reevaluated in terms of how we pay for the value that's brought by, say, the stabilizing aspect of other assets on the grid. And a policy change on the net metering side would drastically increase the number of homeowners that are looking at residential energy storage systems to complement their rooftop solar and really taking their homes kind of off grid.
Good point. So you touched on scale, and we have a question actually dealing with that talks about modularity. So modularity is seen to be an advantage of lithium-ion systems, and that you can make small batteries, you can make large battery systems. Then you can install them in different applications and spaces. So when we talk about hydro or pumped thermal or hydrogen systems, how does modularity play into that? Is it not a factor because you got to go big for economy, or do you have modular options with these spaces? And I'm going to start over with Ben again on the thermal side. Sorry, you always get the least time to think.
I think modularity opportunities are there, and it's that's part of the design for cost that every technology undergoes. When we're even for large scale systems and deployments at 100 megawatt scale, when we're talking 300 to 900 gigawatts of energy storage that need to go on the grid over the next 10 years, that's a lot of installations across a lot of different technology types. So the orders of magnitude that we're talking about across the entire electricity sector scan many orders of magnitude. And I think there's opportunities for modularity across all of them.
What, just for your particular system, Ben, I gather you take the sweet spot to be the 100 megawatt, 10 hours of storage that you're looking at. Is Malta expecting to go larger than that, smaller than that? Where's your next change in scale?
Individual projects can be tailored up or down slightly for application. I think there are economies of scale that we want to get to first before going into drastically different product sizes, for example.
Okay. David, on the pumped hydro side, what's your bound on scale for these systems? Does modularity make sense in a pumped hydro system?
There is a certain amount, but it's probably not as high as could be seen elsewhere. And particularly, you mentioned the battery side. You can have a variety of power per unit, for example, between 50 and 450 megawatts per unit. That's possible. And so we can build some modularity in. Nevertheless, it's true that each site does have its specificities. And so a lot of the products a lot of the projects are custom built. One area that might be of interest to mention, so I talked before that China is putting a lot of pump storage in, and they're typically wanting units of 300 megawatts and 4 units. So each pump storage power station is 1.2 gigawatts. And so they've got certain blocks of power, and that leads us then to a certain almost standardized form of design. So if there's sufficient volume, we could start to get there. But for the moment, it's a little bit more custom built.
Okay, and that's a good point. Putting in multiple power blocks gives you some flexibility with respect to scale.
Yeah.
Jean, you want to comment on modularity with hydrogen?
Yes, I do. Conversations with providers is key. I can give you some examples not in the SMR world, but in the electrolyzer world. A 100 kilogram a day electrolyzer in 2012 has been replaced by a 2,000 kilogram a day electrolyzer today with less cost. And so if you had bought 10 copies of 100 kilogram a day electrolyzer in 2012, you would be looking at more upfront costs, more O&M costs, more insurance, and more labor. But if you waited about 9-10 years and put an order in, you'd be surprised at the cost differential, including the operation and maintenance costs and insurance costs. So yes, modular, yes. The providers, for example, for electrolyzers do have their design optimizations, which they base on years of field experience, years of load balancing, years of looking at what grid storage requirements are out there, and then they optimize so that they can provide a design with the least amount of engineering costs, the least amount of operation and maintenance costs to the end user. So they'll make a module, copy it into a box. So I recommend to get a hold of that, one has to constantly be in touch with the supply chain to make sure trends in size are known and certain.
David's got a question or a comment.
It's just a comment, and let's deal with everyone's questions before we come to this one. But I'd just like to bounce off what Jean said. If progress is so rapid, sometimes customers come back and say, well, I'm going to wait a few years.
Yes, no one wants to be the first. They want somebody else to take that bullet. Okay, so modularity is almost an attribute of batteries, but then is there an upper bound that you run into trouble because you can't scale these things up? I mean, do you have to have a zillion cells if you want to have a 100 megawatt battery system? Is that a problem on the battery side?
Indeed, correct, great point right there. That's when you have a module, if you look at each battery cell so small, you need a billion of those, then that might affect your scaling issues. I agree. It's a balance right there. However, people need to look at this carefully. If I look at lithium ion probably will need this type of form factor right there, because you look at the manufacturing is very precise right now. Anything deviated away from that can cause safety concern, right? And there I will argue this might be something lithium ion going to the grid scale, very challenging problem for lithium ion because of manufacturing precision is so high. And you go to a billion cell, it's very likely you're going to have a few cells that can run into trouble, that can trigger the bad problems. So then I will argue, I don't mean to continue advertising nickel hydrogen. Nickel hydrogen electrode is very thick, it's millimeter thick instead of 50 micron, right? Much thicker, sapphire is much thicker. The precision is you hand put it together is already sufficient. So I will say, well, for grid scale, actually, whether modularity is entirely the benefit might not be. If you look at band system, right, or pump hydro, I mean, this system can go so big that's a benefit. Certainly you don't want to put it close to neighborhood, but why do you need to put it close to neighborhood? You don't really need it for most systems. You don't really need it. I think it's a benefit of other technology of the scale that lithium ion does not have in terms of form factor. So,
yeah, I agree. There does seem to be a natural complementary nature between battery technologies in general and things like pumped hydro and the thermal systems that are designed for very large scale.
Yeah.
Hydrogen I view as kind of straddling that line because you can have, small fuel cells, and you can have larger hydrogen fueled turbines. So maybe it has a little bit of a different role there. So we got about a little under 10 minutes left. Let me ask if Sarah or Nate wanted to comment on this last round of discussions, and then we'll have a wrap up.
I was just going to say, I think that in addition to modularity and scale up, one thing that we haven't mentioned today is the perhaps positive and negative synergies between, for example, the grid scale battery market and the EV market and the consumer electronics market, all of which continue to grow and continue to push technology development in the battery space in particular. And I think that the connection points between pumped hydro or hydro generally and things like floating PV, and those hybridization concepts could also help scale up some of these other technologies as well. And so, I think if the CSP market is to grow, that would help the Malta activity there. So I think thinking in terms of not just modularity, but also scale. And the last thing I'd say is that there is, in addition to sort of modularity, there is, doing things a lot of times, even if they're somewhat unique. I think the price of a coal plant in China is much less than that in the US because they're cookie cutter plants. And while they're not really modular, they're all the same. And I think the more we can get to that, because what our data shows is that the amount of storage we're going to need is really large. Especially if we move quickly to a very high level of renewable capacity. And so the market is going to be large, and it's going to be able to absorb a lot of efficiencies of manufacturing.
Right. Yeah, very good point. Yeah. It may not be we don't need the best answer necessarily. We need a good answer that's going to address a lot of these things. And there's going to be a lot of different answers.
Yep.
So there were a couple other comments in the Q&A, not really questions. Michael commented that Taco Bell is allowing free charging now, and they'll even bring your food out to your car while you're waiting. That's handy. And there was a comment about, the challenges of garage usage in California hasn't stopped California from being one of the largest adopters of EVs across the country. So I think it's been my experience as well, when you actually drive an electric car, it has some unique advantages versus what we're used to that you really have to just experience to recognize. All right, I want to thank the panel for participating today. It's been a somewhat lengthy session, but we had a lot of great presentations. There's a lot of synergy and complementary nature to the different technologies that were discussed. So I think there's much work to be done. And I would say that's a very exciting time to be in the area of energy storage. And I'm looking forward to more of the same. My own area is in thermal energy storage, and I'm particularly interested not only in thermal energy storage to make electric power, like Ben is talking about, but thermal energy storage for thermal users, I think, is an area that we're going to see more of as we seek to decarbonize the entire energy sector. So let me leave it open here if anyone has a parting comment that you would just like to make before we wrap this up. All right. Well, hearing none, we'll adjourn and let people go about lunch. I guess it's about that time for much of the country, depending on where you're signing in from. Thank you all.
Thank you.
Thank you, Craig.
Thank you, Craig. And thank you to the entire NREL team.
Yeah, thank you all. We did record this presentation and we'll share it in a couple weeks.
Thanks, Rebecca.